Cool. Alright, so for those who don't know, I'm Sean Dembo.
Brandon Clark.
So the project we're working on this semester is Dr. Memory. Worked on it last semester, so Brandon's joining me this time. Start off, so probably a lot of you don't really know what Dr. Memory is, so Brandon's going to explain what it is and what we're contributing to it.
Alright, so Dr. Memory is a debugger for 32-bit applications on Windows and Linux, and it will look for memory problems, which I'm sure most of you have used Valgrind in data structure, trying to figure out why when you print a list it comes out as squiggly square $sign instead of ABC. So it's just going to detect different things like you trying to access memory that isn't yours, that's been freed, trying to modify values that aren't really there, it's just an empty memory location. And it's going to tell you all these things much the same way that Valgrind will, but faster. Okay, so how it works and how it does this is it's going to use a thing called shadow memory, where it's going to take everything that all the memory the application is using and kind of do like a RAID 1 type thing on it, where it's going to do it like again over here. And so you're going to kind of have two of the same things, which will in effect slow down the application. But and in that shadow memory, it's going to assign like one of 3 different states of them: unaddressable, and uninitialized, and defined. So unaddressable would be if you had a chunk of memory and then you freed it and then tried to access it, it's going to complain about unaddressable access because you're not supposed to access that memory because it's not yours anymore. So if you free something up, then it's going to put unaddressable on that, and then if you access it, it's going to complain. And then uninitialized would be if you created a variable, say x, and then you tried to do like a comparison statement against it. You didn't put anything inside of that, so it's going to complain about you trying to access a value that isn't really there. And then the other one is defined, where you do what you're supposed to do, and you put a value inside that block, and then you use it. And it's going to monitor everything that you do from reading and writing memory. It's going to do it in the shadow, and then it's going to do allocation, deallocation, and everything that associated with memory. And then there's also these system calls that are important because when you have an application, it doesn't really know what's going on in the kernel, so it needs to utilize these system calls in order to work. So the problem with this is that the application doesn't really know like what's going on, so because Dr. Memory is copying it, it doesn't really know what's going on either. So Dr. Memory needs to have like a big database of like how to use these system calls in order to use it system call in the shadow memory, so that is an exact copy of the application. So what me and him are doing is we're looking at the Windows system calls and trying to put those in the database so that it knows what the different parameters are for the system calls. And for Linux, that's easy because it's all on the internet, but they're not all there for Windows.
So last semester I worked on the advanced local procedure calls, which is kind of Windows inter-process communication. So the main thing we're working on this semester is the NT WOW64. So I'm just going to give a little background information onto what WOW64 is. So on Windows, if you want to run a 32-bit application, you got to remember that the syscalls are all 64-bit. So this WOW64 is kind of the emulation layer. So it's implemented with 3 DLLs. So if you actually run a 32-bit, these are loaded up. They're the only 64-bit DLLs loaded in your process. So it's pretty much what it does is it saves your 32-bit context state before it switches into a 64-bit mode. So that's what WOW64 DLL is. Then the CPU and the WOW64 Win is your GUI, so that would be Win32K sys. So that driver handles a lot of the GUI syscalls. So I'm just going to go into the convention. So if you're debugging some application and you hit one of these syscalls, this is what you're going to see. This is the convention. So you move your index into EAX because any syscall you make right before it switches. But what you really want to focus on is this call into the F segment at offset C0. This is in your TEB, which is the thread environment block. That just includes information for your running thread. So it's mostly null, but at this time it's going to get propagated with a pointer, which is going to point into this WOW64 chunk, which you can see over here, so the WOW32 reserved. And this was first coined in 2009 as Heaven's Gate, because it's a far jump. It's actually really cool if you go through this on a debugger. So at this point, if you follow through this jump, you're actually going to transition into 64-bit code. So you're in 32-bit, transition into 64-bit, and at this time you're able to actually perform just a normal sys call. So it's actually pretty cool. So if you guys want details on how to actually debug that, you can actually see the jump. So it's kind of cool. I don't want to get too much into it. Anyways, so this is what our main proposal was on, working on the NT-WOW64. So I started on that already. Reversing it was actually pretty easy. A lot of them were the same. So if you actually go into the WOW64 DLL, you can pretty much see that NT-WOW64 will call the NT read, but it has to change these 32-bit values into 64-bit. But now I need to actually integrate this into Dr. Memory. But to do that, I need to add in special handling, since a lot of these are 64-bit values and Dr. Memory doesn't support that, so I have to add in special routines for that. So that's just a rough overview. He's actually going to start working on the worker factory class of syscalls, and hopefully we'll be getting those in soon. Any questions? All right, thank you.